Okay, everybody, welcome back. So, got an example, wrap your pipes, mostly because I've had issues with condensation causing rotting damage in my house. So, make sure your pipes don't have a bunch of condensation. So, what does it say? Well, it says steam at 40 degrees Celsius condenses on the outside of a 5-meter long, 3-centimeter diameter, thin horizontal copper tube. Okay. The thin right there is simply saying that the copper tube doesn't have some sort of temperature gradient. The temperature on the inside is equal to the temperature on the outside. That's the assumption we're making. Water enters the tube at 27.5 degrees Celsius, an average velocity of 2 meters per second, and leaves at 35 degrees Celsius. Okay. So with that, I can see that it has a change in temperature. The velocity doesn't change, so the kinetic energy doesn't change. It doesn't say it goes up or down, so no potential energy changes. And with this, it seems like the water is being heated up as it goes through it. Then it gives me some information about water at room temperature, as well as the enthalpy of vaporization, which is going to be very helpful to us later on in the problem. So let's get started. First thing I always like to do is draw the setup. Beautiful. This looks like oil more to me than water, but I'll forgive them for that. So I've got steam on the outside, it's condensing. I've got water going in, and then water going out. Now I'm going to write out our energy balance. So my change in energy with respect to time is equal to my energy out of the system with respect to time minus my energy into the system with respect to time. Now, this is a steady system. As such, the change in energy is going to be 0. Because yes, this water is heating up from here to here, but that's happening inside my control volume. Everything is constant within that control volume. So if my change in energy with respect to time is 0, that means that energy out is equal to energy in. Now I've got to figure out, well, what is the energy out of the system? What is the energy into the system? Well, energy out is going to be equal to the condensation, and energy in is going to be the energy from the water. So water is bringing energy in. Condensation is also removing energy. So if I have those two, I could probably solve this problem. Now, how am I going to calculate those? Well, these guys are always just m times h. Now, if I'm doing a change with time, I'm probably going to have a change in enthalpy, but we'll see that soon. So for water, I have that the water goes in here at one temperature and out here at another. So I have a change in energy with respect to time. Now, it also gives me a specific heat, which means I can use it. Nice. And we're assuming constant specific heats. So H2 and H1 just turn into constant specific heat, constant pressure times temperature 2 minus temperature 1. And as a note, you don't actually have to convert those temperatures because temperature difference in Celsius is the same as temperature difference in Kelvin. Now, an issue I run into is I don't actually know what the mass flow rate is right here. And since I don't know the mass flow rate, I have to calculate it. That's not difficult. We've seen it a lot of times before, which is it's simply equal to the density times the velocity times the area. Now, I didn't write this out here, but the density is given right here in the problem. The velocity is given right there in the problem statement, 2 meters per second. And the area is going to be this right here. So pi over 4 times 0.03 squared. And if I then plug that into my equation for the heat of the water, I can have 44.17 kilowatts. Okay. Probably wondering, what about condensation? We'll come back there. We'll come back to that in a minute. So first off, when calculating the condensation, you might be wondering, well, what is this? And why didn't we calculate it before? The answer is, we did. That is the same thing. Because we said that energy out is equal to energy in, we said that the energy change with time is condensation, energy change with in is water, and so they're going to be the same as each other. So I actually already did calculate it. Surprise. And this is going to be equal to the mass flow rate of the condensing water, condensing steam, times the enthalpy of vaporization. This simply says how much energy per kilogram does it take to take it from being a saturated vapor all the way down to a saturated liquid. So I can solve that, and I get 0.0184 kilograms per second. I've got my answer. Everybody's happy, and we're good to go. Well, thank you all for listening. I hope this helps you, and I'll see you all next time. Bye-bye.